Good day, dear friends. My name is Evgeny Proskrin. I'm the founder of A.T.F. Group. This is an engineering and manufacturing group of companies that started in a garage, producing hardware for transformers. And now it offers digital solutions for a wide range of industrial sectors. Today we are launching a series of micro lessons to share practical knowledge and help our energy sector operate more reliably, efficiently, and safely. After all, our mission is simple: your energy under our protection. In the previous module, we explained how to connect transformers in parallel and why the connection group must match. Now we go further. We'll examine how load currents are distributed between transformers, why imbalances occur, and how equivalent circuit models help engineers analyze transformer behavior. The problem of unequal current sharing. Even if two transformers have identical rated values and are connected correctly, their load currents may not be equal. Why? Possible reasons include slight differences in winding resistance, variations in short-circuit impedance, unequal operating temperatures which affect copper resistance. Why does this matter? One transformer might get overloaded. Phase balance may be disrupted. Risk of system failure and reduced reliability increases. Load distribution formula. When two transformers are connected in parallel under the same voltage, the share of current each one carries depends on its relative impedance. The rule is simple. The transformer with lower total impedance will draw more current. This includes both the winding resistance and the leakage reactance. Correcting current imbalance. To equalize currents between parallel transformers, engineers can use additional series reactors to raise the impedance of the stronger unit, load tap changers or OLTC to adjust voltage and balance power flow. Specific connection strategies that take impedance differences into account. Equivalent circuit of a transformer. An equivalent circuit is a simplified electrical model of a transformer that includes winding resistance, leakage reactance, core loss resistance, magnetizing reactance. You can think of it as an electrical portrait of the transformer, showing all its internal behavior. This circuit model allows you to calculate power losses in the windings, output voltage under load, fault current during short circuits, three-winding transformers and autotransformers. These devices are more complex. Load currents are distributed among three windings. Mutual inductance between windings becomes a key factor. Backward and cross-coupling effects must be considered. The equivalent circuit becomes more detailed, but the basic principles remain. Impedance defines current paths. Each winding affects the others. Practical task. You have two transformers operating in parallel. The first one is rated at 630 kilovolt amperes. The second one is rated at 1000 kilovolt amperes. Which one will carry more current? How could the current be equalized? Write your answers in the comments. Conclusion. Today you've learned why current sharing is rarely equal in real systems, how winding resistance and impedance affect load division, how equivalent circuits help analyze performance and reliability. In the next module we begin Chapter 6, the insulation system of a transformer. We'll cover material choices, aging effects, and how to test dielectric strength. Want to explore the topic in more depth? Visit our website. The link is in the description. Interested in real-world solutions and industry challenges on this topic? Contact us. Our details are on the screen. Want to become a part of the global energy flow? Reach out to us. You'll find our contacts on the screen.